get started. It's 10 o'clock, so we can honor your time. Welcome back, everyone. I'm pleased to introduce John McGann and Doug, say your last name for me.
Stingelin.
And they are going to speak to us from GLHN Architects and Engineers. Take it away, guys. Thanks.
Okay, thank you, Jenna. Hopefully everybody can hear me. Good morning, RMA. I'm glad to be here this morning. John and I, first of all, my name is Doug Stingelin. I'm a director of mechanical engineering at GLHN. My co-presenter is John McGann, who's our civil engineer. John, you're also a graduate of University of Wyoming, right? That's right. Okay, I'm thinking that's one reason why we got selected for this presentation. But anyways, today we're going to talk a little bit about thermoplastic piping. It's a special type of new technology piping that's out there. If you watched Bill Roth's presentation, I picked up on the word limited capital and dollars and the challenges with acquiring those funds. And if you've attended a lot of the RMA sessions in the past, a lot of the topics on deferred maintenance came up. Also, utility infrastructure, a lot of campuses considering new utility distribution, underground piping, expanding, maybe converting from steam to hot water. I think this presentation will suit you well. Okay, so when I started my career out at GLHN in the late 90s, and when I first went into the mechanical rooms, I was instructed to look up and take notes, and most of the piping that I saw was either steel or copper for forced pressurized distribution systems like hot water, steam, and chilled water. A lot of work involved with pipe fitting and welding, and sometimes we used mechanical couplings, but the work was very involved. It was heavy pipe, and that was kind of the standard. Throughout the years, things are starting to change. John and myself have had a lot of experience with new types of technology with plastic piping. And I think that's because the technology has improved over the years. Some of our old fears with piping not holding up for pressure or can't take heat, maybe expandability. A lot of technology has come a long way to mitigate those types of things. We're seeing plastic piping everywhere now. Underground piping, lots of campuses are using plastic. HDPE piping, a lot of that in the ground. A lot of buildings on the plumbing side, even on the HVAC and chilled water, are looking at PEX piping, smaller diameter. Yeah, we're starting to see a lot of it. I think a lot of the contractors and developers have adopted it, and I'm curious to know if some of the higher institutions, education institutions, are adopting these technologies. Fire up the chat if you can, and we'll get some comments going. But I think the big message we wanted to deliver today that, there are alternatives out there to traditional steel, copper, metal-based systems. Not that there's anything wrong with it. They're tried and true, and we've used them for decades, right? But like Bill Roth was commenting, we're faced with material shortages, costs, all types of different metrics that we're trying to deal with today, and we're looking for logistic alternatives. And in our opinion, there's definitely some logistic alternatives with different types of plastic piping, as long as you play by the rules and within the scope of design. Okay, so we've broken today's presentation out into kind of three pieces. I'm going to talk a little bit about a particular type of plastic piping called thermoplastic piping for primarily building applications. And then John's going to jump in and talk about more site distribution applications. We've picked 2 or 3 different types of piping we'd like to talk about because we have actual experience and have learned a lot of lessons and key points that we wanted to share with the group along the way. So plastic piping is everywhere now. And just like many institutions, there seems to be an institution for just about everything. In fact, there is a Plastic Pipe Institute, which is a great resource for all types of different types of plastic piping. What we'd like to talk today, particularly, we're going to talk about HDPE piping for underground burial piping, PERT also for underground. And then for indoor, we're going to talk about a polypropylene R and a PPRCT. These are kind of new technology that's was fostered to fruition in Europe. Now it's back over here in the United States, and we're starting to see great applications. The big story is, plastic piping's lightweight. It doesn't really have much of a kryptonite. Um, the only kryptonite it really does have, obviously, is pressure and heat. That's always been the considerations. But a lot of our fears in the past about brittleness and under pressurization and pipe breaking and leaks and strength, uh, with the technology we got today, a lot of that is being taken care of. Okay, so thermoplastic is a type of piping basically that if you melt the ends of the pipes, you can weld the pipe together, a plastic weld. And the weld often is stronger than the actual pipe itself. Um, the real technology is in what we call copolymers and resins, and all the brands out there kind of have their own unique take on that. The polymer is really talking about the physical strengths, properties of the pipe, getting the brittleness out, making it more ductile. The resin are these additives that are impregnated into the pipe to really raise the temperature and pressure ratings. So that's kind of where the technology is going. Okay, so let me jump into building systems piping. I'd like to talk in general about polypropylene-based piping. R stands for random. That's what most manufacturers offered. Some other manufacturers, their selling points are, well, we sell PPRCT. It's extra science that's built in to even further raise the temperature and pressure resistance of the pipe. So I'm going to kind of use these PPR in general, RCT in the same tense for this presentation. Okay, so PPR and PPRCT piping, our experience, great for potable water systems inside buildings or underground, great for chilled water, domestic hot water, domestic cold water, processed water. These are all super applications for it. It seems to work well. You can install it in plenums as long as you insulate it. It can be outside. You can shield it for UV protection. And of course, you can bury it too as well. I would say on the hot utility side, steam condensate, it's just above the temperature and pressure ratings. And it will never be there with plastic piping. And really, there's a limit on the hot water temperature. I'm talking about heating hot water temperature. 180 is in general the kind of the tipping point here, but really we feel more comfortable around 140 to 160. It's all really dependent on the pressure and temperature you have. Of course, you could acid waste and waste systems, probably better to go with a standard type of acid waste system, an O'Brien system, for example. This is really for pressure piping, PPR and PPRCT. There was a few manufacturers in the past. Now there are a lot. Most of the piping is still produced overseas, but that is changing. A lot of the companies that are based in Europe and across the world now have production facilities in the United States, which is certainly improving the source of materials and making it more readily available. PPRCT is kind of the newest version of polypropylene piping. In this picture, you can see it's kind of a composite pipe. I'm going to talk about that in a little bit, but PPR in general, the random copolymerization is what's changed over the years. It's allowed the pipe to withstand higher strengths, higher pressures, and higher temperatures. Um, I think what PPR piping in general is excellent for is corrosion resistance. Um, if you do it and you set it up correctly and you make your welds correctly, it's basically a leak-free system. It definitely has some advantages for material and labor cost. I mean, think about it, right? The pipe is very light. Two guys carrying a 10-foot stick of pipe that's 14 in diameter can just carry it by themselves. Not much rigging needed, very simple. And the problem with old plastic piping systems, when you heat it up, the growth in the piping, the lengthening when you heat it up was just big. But now we've got technology in the material makeup of these pipes that really restricts and mitigates that growth, such that you can use it in higher temperature applications. The polypropylene side of the piping industry is not new; it's been around. What has been new over the years is development of the PPR um, offshoot, and really that, again, that was for strengthening and temperature and pressure. Another big thing about the PPR, as opposed to other older types of plastic piping systems, is that it's ductile. Um, I can remember a time when we had direct varied piping with standard PVC C900 pipe. We were doing a pressure test. It's a brittle type of pipe. When you over pressurize that, it basically explodes into fragments and bits and pieces. It's a dangerous type of situation. That doesn't happen with a PPR based system. It just doesn't expand and destruct in a similar fashion. The big difference when you're selecting thermoplastic piping versus standard copper and steel. Steel and copper, American based piping, domestic, it's all inside diameter controlled. Whereas the plastic piping, which is basically fostered to fruition in Europe, is all outside diameter controlled. And really, the critical metric you need to know is the diameter ratio. Some people call it standard diameter ratio. And basically, the thicker the wall you have, obviously, the higher pressure you can take in the pipe. Um, that's generally how it works. And of course, it's all in millimeters and not in standard increments. That's not a problem, though. A lot of times we place on our drawings tables, just if you are happening to specify different types of piping, copper, steel, also some thermoplastic piping, you can put equivalents on the drawing. We typically don't put millimeters on our sheets unless we're working outside the US. But the products are available from a 1/2 inch through 24 in general. Again, same thing. I usually plaster tables on our drawings. It really helps the contractor and the owner understand how to specify multiple types of pipe on the drawing, with the hope that you can go through the value engineering process and pick a pipe of your choice that's going to make the scope and fit your budget. We've done a lot of hot water, domestic cold water piping for dormitories. We've built similar tables for the plumbing contractors in fixture units and GPM. The diameters are different, and you got to understand the flow considerations are slightly different. But it's easy if to go by just putting conversion tables on your drawings to go from thermoplastic to copper to steel or even PEX piping. PPRCT piping, for example, is one product offered by Aquatherm. Aquatherm is one of the more robust manufacturers who've captured a pretty big market share of the PPRCT market. The cool thing about the PPRCT is it's a composite pipe. And what they do is they've impregnated like a fiber composite layer between two standard layers of PPR piping. And the benefit of that is it really curbs and mitigates the linear expansion. It's still not as good or as small as copper and steel, but it's manageable. That way we can start running higher and higher water temperatures in there, and you can control growth a little bit better. Just for comparison, here's a table from some PPRCT piping. The left column is basically delta T from your installation temperature. So, for example, if you install on a cold water system or a domestic hot water system at maybe 60 degrees, and you're adding your 50 or 60 degrees, and you're getting up with a delta T of 100. If you use PPRCT piping, you're for every 100 feet of piping, you're still growing 2.3 inches. That's not as much as copper or steel, but standard uniform PPR piping is probably double that at least, or even higher in some cases, which makes it harder to control linear expansion. In buildings and even in site utility distribution, you still have to control expansion growth. And you can apply similar methods that you would use for steel and copper pipe. For example, maybe every 150 feet of linear pipe, standard practice is to do expansion loops, where you basically peg, at the start and the beginning, you put an anchor, you put some guides in the intermediate locations, and put a big U-bend in, then that can kind of expand and contract. You can also you can also use expansion joints as an alternative. L-bends are also an option, similar, using different mechanical devices with anchors and guides. Anchors are very similar to what you'd see in steel and copper systems, but they're much less light. They're much lighter and less robust. Basically, to restrain and the forces from expansion on the plastic piping, it's orders of magnitude less than it is for steel and copper systems. You really just have to clamp down tightly on the piping. They do make specialty type of anchors and guides that can do dual purpose. For example, this is a product you can purchase from Bismat. It has little spacers in there that, if you want to make it an anchor, you can take out the spacer and really cramp down on the piping, or you can leave the spacer in and leave it like a pipe alignment guide. We've had a lot of experience with this. For example, this is an installation of a pipe anchor where we've clamped down on the pipe, and the supporting structure is anchored to the concrete deck above. Guides you can buy from different manufacturers. We've bought some guides from Mason here, but it's a same approach. It gives movement left and right, allows the pipes to move longitudinally, and just hugs the pipes and lets it grow. The big thing is you don't want to dig into the plastic pipe because it mars and scratches really easily. Same thing when you got risers in the pipe and you're coming off for your lateral branches. You really want to try to create allow for movement in bidirectional paths. Sometimes that kind of manifests into a picture like this, just providing offsets. So in our notes and details, when we put on drawings, we always try to say, install in a straight and parallel fashion. Well, after it heats up a little bit, especially on the hot water systems, expect some bending. That's just par for the course on these types of systems. Okay, so the big picture again with plastic and thermoplastic piping is pressure and temperature ratings, which are directly related. I've kind of circled the bottom end here. again, for building applications, 140 degrees is kind of, where we typically limit our work. Domestic hot water, new buildings, we're not designing to 180 degrees anymore. That's kind of where we stop. I think that's kind of our safety. There are other types of plastic piping materials that can go higher in this, but based on our experience and the materials we use, we typically limit it that. Um, it's important, really, if you try to do higher temperatures, that you have safety controls in place, because you will damage the piping and accidents do happen. The types and products of thermoplastic piping that are available, they've all been certified through ASTM and the different certification testing labs, and everything has been adopted here in Canada and the United States throughout the building codes. The stuff's legit and it's been around. Pipe fittings, I think you can buy pipe fittings from each different manufacturer. I think that's where they make a lot of their money, honestly, is on the different types of piping systems, um, um, pipe fittings that you can buy. And really, thermoplastic piping, you can join three different ways. You can do fusion joints, which is basically welding, either a socket butt or saddle joint. Non-fusion, you can have threaded fittings that it can be impregnated into the actual pipe fitting, or you can do standard flanges that made up to copper or steel flanges. Um, and of course, sometimes I'm going to show you in a little bit here the machinery that you need to do the butt welding. Sometimes you really can't do that, and you can use standard electrofusion joints. For example, if you have a hard to reach place, this is a technology you can do to make those types of joints. Okay, so how do you actually join these pipes? Um, Most contractors will either purchase or rent um, equipment that can do the job. Um, these are basically racks where you can cut. They look like uh, meat or cheese grinders, kind of cutoff saws that are intermixed with welding irons. So the slicers cut through the pipe. There's a deburring type of feature, and then these jigs where you can slide two pipes of pieces together. They mate. They have a big iron in the middle. You plasticize the pipe, and then the actual jig pulls the piping together. That's in general how you mate thermoplastic piping. Just real quick, for 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 joints with parts and pieces, fittings, you can do socket joints. Pretty simple. You have an iron that heats up the socket joint, um, and then you simply slide the piping in and let it cool. It's really simple, as long as you follow the directions and you do it right. Saddle joints are real easy to do. You make a drill a hole. There's a special iron that heats up the base material so that you can just insert a joint and let it cool down to make a fully welded connection. And then there's standard butt joints, like I just talked about before. That's kind of the deli slicer with in a jig that will pull the piping together after it's heated and cooled. Hangers for thermoplastic piping are definitely a little downside on that, I think, just because, as you know, with plastic piping, it's not as rigid as steel or copper. And generally that means you need more of them. For example, when you're working with higher temperature water in plastic pipe, you might maybe every 4 feet, if you're heating up your water a delta T of 100 degrees or more, you may have to put in a hanger every 4 feet. That's just kind of how it goes. But as your DR gets smaller, your pipe thickness gets bigger. Of course, the spacing goes out, but you're definitely going to put more pipe hangers in than you do with standard steel or copper. So I mentioned before that you can purchase specialty hangers from different manufacturers, or what we've done, you can buy standard clevis hangers that you'd use on any type of piping system. The difference is you want to add Teflon tape or some sort of rubberized surface on the pipe hanger itself so that the pipe doesn't rub and scratch it and mar the piping. Pretty standard practice. This is definitely a way to economize inside buildings. Fire stopping, just like any steel or copper pipe, you have to maintain your fire penetrations. Now, as far as the plastic piping goes in ceiling plenums, that's no bueno unless you wrap the pipe. That way you can attain the combustibility and smoke, flammability and smoke limits that's acceptable. Okay, we got a question that came in. Doug, can you speak to any certifications that an installing contractor should maintain for quality install? Well, I could speak to, for example, Aquatherm, for example, is one manufacturer that does their own training and certifications. They'll put your crew into a course and make sure that you understand the process and you could demonstrate that you can install these systems. I'm sure that's certain for other manufacturers as well. Is there one that fits all? I'm not sure. I'd have to look into that. Okay, one more question from Todd Scott. Without getting too technical, if possible, can you explain how the weld is stronger than the pipe itself? I can try to explain. I don't really know the answer. I do know that just by plasticizing the joint, the cross-linking in the piping and the polymerization is stronger than it is just in the standard extruding process. John might be able to speak a little bit better than that than I can. But anyways, I hope that answers at least part of your question. Okay, you're welcome. Okay, so to switch gears here, I'm going to pass the mic over to John, and he's going to talk a little bit on utility distribution piping.
Good morning. As any campus, there are a number of reasons why you select a certain pipe based on your actual conditions, crew size, how you're going to maintain the system, etc. So there's not one and only pipe that fits all projects, but would like to talk about the HDPE and the PERT piping in distribution systems. Go ahead. Basic difference is that the PERT has a raised temperature limit, normally operating up to 180, but can accept intermediate or intermittent temperatures of approximately 203. It can come in 40-foot sticks. It can come in pre-insulated. You can insulate it with gilsulite, etc. So a lot of the combinations of insulation that you use on other types of pipe is also appropriate for these thermoplastic piping. The picture on the right also shows that with the flexibility of the piping, it's possible to take a number of 40-foot joints and fuse them all together, and if required, do a preliminary test on the ground before you either install or pull through a boring. Go ahead.
Did I lose my thing here? 1 second, folks.
So both projects or both products are suitable for a number of distribution systems on campus, hydraulic system, potable water, chilled water, etc. As Doug explained, probably the limiting factor is the temperature aspect of with the PERT. Operating pressures are controlled by the temperature, which is usually limited to 180 degrees, which could be suitable for a lot of low temperature or hot water systems, but not for condensate return, etc. There are some systems that are the PE RCT that will allow you to go up to about 230, but there's a whole variety of thermoplastic pipes that we can look at, but these are the general ones that we have worked in the past. As Doug indicated, that some thermoplastic pipe comes as IPS controlled, that controls the outside diameter. So as you increase the wall thickness, or the DR, which is the ratio of the diameter to the pipe thickness, your interior area decreases. That is a consideration in design. Some manufacturers, particularly in the HDPE realm, also make ductile iron outside or inside controlled pipe, which gives you a different variety. It doesn't mean that one pipe is better than the other. It's just a design parameter that, based on the type of piping you use, you fully consider what is the flow area of the pipe. This kind of gives an example of various inside diameters for various types of pipe, steel, various DRs for HDPE, and you can kind of see it changes as you go. That does not mean that one is better than the other. It's just when you call it out, you have to be definitive on what is your DR, as well as is it outside controlled, or is it DI inside control in your hydraulic calculations. Pressure, as all thermoplastics go, as temperature increases, the working pressure decreases. As you can see, from a change in DR7 goes from about 300 psi at 68 down to 167 at 180. So basically, as you increase the temperature, requires you to decrease the DR, or use a thicker wall section to accommodate for that expansion, or that loss in strength. But one kind of unique thing is that while there's a high coefficient of expansion, the elastic modulus in HDPE pipe is substantially less. So if we kind of look at an HDPE with a delta T of 40, the expansion is almost 8 inches. But the force to control that expansion is less than 400 pounds, as compared to 1,300 pounds required in a steel pipe. One of the things in distribution system is that you can induce some of that forces in the pipe itself, just like you would do with a ductile iron restrained system, and allows for some snaking in the ground to accommodate that. So while it expands greatly, probably the key is looking at the expansion at joints and bends, that you're not stressing one or the other. But it should be noted that the force is substantially less than you would experience in ductile iron. Typically, along HDPE pipe, you can use the soil friction to restrain some of that force that is developed during expansion. Connections can be made with either fully butt welded fittings all the way through, or a combination of fittings and mechanical style joints that are restrained to allow you to handle the connections. basically what happens is you allow to make the majority of the dips or crossovers up on the top of the trench and either connect with couplings on either side or actually use ductile iron fittings as required. Typically, there's no requirement for thrust restraint. One area that you need to pay attention to is at connections to existing system. If you're connecting to a existing ductile iron system that is not joint restraint and you have a long section of HDPE coming into it, you may have to put a restraint on the interconnection so you don't pull the joint out when the HDPE shrinks. As with the other pipes that Doug talked about, there are a number of connections, fully butt welded, which actually takes one section of pipe to the other. You can see on the right, they are doing a joint in which you plane the joints so you have uniformly around the connection, heat it up, and then pressure bond it together. But also there are electrofusion, which has electrodes in the couplings, etc. There are some saddle fusion techniques. Molded fittings are available, but typically under 12 inches. When you get into larger fittings, they're often shop manufactured and of the same DR or maybe one DR larger. Mechanical joints are available, as we saw in the previous picture, which can be connected to your standard gate valves, air valves, expansion, or whatever you need to, and they are available in both slip-on and restrained style joints. One thing you need to pay attention to is when you're using mechanical joints, sometimes the HDPE tends to creep over time. So when you look at a selected fitting, some recommend a stiffener underneath to prevent that creep over time and loosening of the MJ style joint. HDPE and PERT are available in insulated and pre-insulated versions. In selecting a pre-insulated version also depends on how you're going to install it. Often when you do a directional boring, you increase the jacket thickness just to allow for a little bit more abrasion as you pull the pipe through. You can use curvilinear alignments, both horizontal and in a boring, dipping down and raising back up. On the picture on the right, they're crossing under a building and a foundation of a tunnel, which were from a sequential requirement of the project, the lines had to be put in before the building and the tunnel were modified. And other you can install by just traditional open cut, jack and bore, and as I mentioned, directional boring. In directional boring, one of the items that you need to pay attention is what is the pullback stress. So when you look at the design of the pipe, you have your typical parameters of pressure, temperature, soil conditions, etc. But one more parameter you need to review is as you put your jack or pull back through the boring hole, which is full with mud, is what is the stress on the pipe as you pull back through. It's just another parameter you need to consider with. Often does not increase the DR of the pipe, but will allow you to cross under a number of obstacles while keeping some of your arterials still in process.
Okay, so that brings us to the end of the underground portion. Now we wanted to share some of our lessons and experiences with you. Why don't you go on mute? 1 second here, folks. There we go. Okay, so some of the big takeaways from our experiences with these types of piping. I mean, the biggest one really is just the comparison, the labor costs associated with steel and pipe, steel and copper pipe. I'm speaking inside when everybody's trying to bring materials off-site, unload them. I mean, most of the time you don't even need forklifts. You can bring them in. The rigging is very simple, and you know, you don't have to be a trained pipe welder, or you don't know how to solder pipe. It's a little more easy to pick up and learn how to install these easier. There's a whole host of fittings out there. Again, I feel like there's very little kryptonite for these types of piping systems other than excessive heat and pressure. That being said, I know there are other types of plastic piping systems out there that claim to go higher, and the technology is only getting better. 180 is kind of the limit. Domestic hot water piping and low temperature heating hot water piping are definitely great applications. Um, there is a little bit involved. You do have to purchase specialized tools, but you can also rent them, which makes it easier and makes a little less more affordable for contractors. You guys have all seen the news about all the shipping containers parked off the coast of Los Angeles. It's getting better. That might be just a current type of thing, but still, most of the suppliers are international, but it's getting better. Domestic production is moving inboard. Costs. In general, for PERT piping, PBRCT piping, 3-inch, that's kind of the changing point. Okay, everything under 3-inch, it's still more. You can still get away with cost for steel and copper, and that's because the material costs for the PERT are high. But once you get over that, logistics get involved, just with rigging and weight and the physical challenges of installing steel and the welding and the brazing. A good resource for this is Gordian, which you may or may not know is a database that was formerly called RS Means. They have a great database in here for PERT piping, for HDPE piping. Those are great, a database if you're looking for a quick understanding of the differences in pipe costs. I like this one. So a lot of the manufacturers, they create their own fittings. Obviously, you need elbows and T's and things, but they also have valves, shut-off valves, and they all make their own hangers. They're all expensive. You don't have to buy these. You can simply transition to typical ball valves or strainers, those types of things, just as easy. Even if you're buying the transitional fittings, it's still cheaper to go that route than to have to buy specialized fittings. And then you also got to think about replacing them in the future. It's easier just to get something that's off the shelf to replace than having to reach out to one of these manufacturers. I'll let John take this one on directional boring if you want.
Directional boring is a unique opportunity to minimize surface repairs. Etc. It's not a one and only selection, but it should be in your toolbox to look at what is your site parameters, what are the site constraints, and evaluate whether the directional boring is advantageous to you, etc. modeling of the distribution system, as we've talked about, is really based on the inside diameter of the pipe, whether you're using any variation of thermoplastic pipes, as long as you account for nominal size versus the actual flow area, it shouldn't be a problem. There are a little bit of improvements in the C factors of HDPE from typically the old core would use 130 for ductile iron, etc., which DIPRA says should be 110. Some of the other plastic manufacturers say you should use 110. Or 100, but I think using a adequate coefficient 110 to 120 should give you adequate modeling with adequate capacity. One of the odd things is that as you do a pressure test in traditional piping, you bring it up to pressure, have the air expelled, etc., and you test at a standard pressure for whatever the test duration and test pressure is. With the thermoplastic is that when you apply the pressure, the pipe starts to expand. So you have an initial testing phase, let the pipe expansion stabilize, then proceed with a following test that will give you the actual calculated leakage or volume of water to make up. AWWA has a standard for that, which is pretty good, but with the HDPE, you have to look at the initial expansion and any potential expansion during the pressure testing.
Okay, so one common miss, because
Hey, Doug, we can't hear you.
can you hear me now? Can you guys hear me now? Okay, apologize about that, guys. See if I can get this back up here again. Okay. Okay. So I'm not sure if you heard the slide or not, but one of the misconceptions about burying piping is that you don't have to insulate it because the pipe has thick wall and an R value of its own. That is definitely a myth. In order to meet standard energy codes, you do have to provide external insulation. Now, it could be thinner in diameter and thickness. You may be able to get away instead of 2 inch to 1.5 inches or something along that line. But in order to meet the energy codes, you do have to insulate your piping. Also, this was kind of a disaster, but I'd love to share with you. Pipe flushing, cleaning is a different animal. When you are slicing piping, you create burrs, and it's imperative that the contractor, the installing contractor, take extra precautions to clean the pipe before they weld it. They take off all the burrs. This is a large domestic hot water application we did, and for maybe a week, we were flushing out the thermostatic mixing valves because they were getting gunked up with the fragments from the actual pipes themselves. So just the lessons learned is to have a robust and well thought out procedure for pipe flushing. Make sure you get your velocities up to get all the plastic pipe fragments out. And of course, again, caution on the hot water side. You need to provide a design that's going to meet the scope of work. Accidents happen. I mean, let's say you don't have a building or a plant and you let the temperature run up accidentally. Maybe one of your failures didn't come into play, or one of your safeties. You know, this particular pipe was designed for 140, and we had an incident where the temperature elevated because of a failed safety, and it got up to like 200 degrees. So it was kind of a combination thing. The pipe weakened, and then there was maybe an inconsistency in the extrusion of the pipe. So the lesson learned here is, you just have to have hardwired safeties. Make sure you're designing with a low temperature system and well within the bounds. Just take the extra step to be prepared so that you don't have failures like this. And then just in summary, I think we're coming down to the end here. The technology is getting better and better. A lot of the fears we've had of the past about strength and weakness and brittleness, and it's getting better, and it keeps getting better. There's more manufacturers on the market now. We've only talked about a handful. There's a handful more. But it's definitely a legitimate alternative, especially if you're in a situation where you need to do value engineering or explore other options. But it's got pluses and minuses, just like everything else. Okay, and that's all John and I had for you today. We do have on our website, you can go in. We've kind of written white papers just to go along with this, so don't worry about notes. All that information is on there as well. Any questions from the audience?
Looks like we've got a couple coming in from chat. So while we're waiting for a few questions to come in, just a reminder that we'll be back at this tomorrow morning at 9 a.m., same format, and you'll use the same link that you had today. So save that in your email or wherever you save things. And it was great to see all of you once again. Jake, do we have access all day to the networking thing, or is that just during the conference? All right, so if you guys wanted to connect, you can send each other chats, but that network button is available. If you had questions for our presenters today and wanted to follow up with them, we have that for the full 3 days. If you wanted to make appointments to network in the platform, that would work as well. All right, Doug and John, thank you so much, and we will see you all bright and early tomorrow.
Thanks, guys. Appreciate it. See ya.
Thanks.
Sorry, man. I don't know what was going on. Like every time I transferred back and forth, the slideshow would go dead. I don't know, man. Whatever.
And you guys are still on, FYI.